Hi, I'm Brian, and for my final lab, I am going to explain the physics behind Full Throttle. In case you don't know what Full Throttle is, it is a ride at Six Flags at Magic Mountain in LA. It is known for having the tallest loop in the world, a 57-meter tall loop. It bolts the cart, or I guess the passengers as well, at an initial speed of 70 miles per hour so that you could actually try to traverse the loop. And I'm going to explain the physics behind that in the later slides. It has one of the longest hang times in the world, right? The longest feelings of weightlessness as you're in the loop for a very long time. And yeah, we're just gonna kind of go through how this ride works. I am going to show a little bit of demonstration so you have a brief idea of what this ride looks like. But essentially, it's just the loop part of it, right? Because that is going to be the main focal points of this presentation. And as you can see, there's that very long stint where they just hang at the top for quite a long time, and that's probably one of the amazing parts. Um, yeah, so the physics fundamentals behind it, right? The main one is going to be that the cart is in a curving motion as it traverses the loop. So we do know the net force is going to consist of two main forces, right? The normal force and the gravitational force, right? On the right, because obviously the force diagrams, right? When it's at the top of the loop, we're going to have the contact force and the gravitational force both pointing towards the center of the loop. And when it's at the bottom of the loop, we have the contact force. And the gravitational force kind of balancing each other out. Of course, we're going to have F net equal to dp over dt, right? Change of momentum, which is also going to be the sum equal to the sum of the parallel components and the perpendicular components. The parallel components is obviously dependent on the speed more, right? Perpendicular component, yeah, is also dependent on the speed and the radius and the mass. Uh, I think another concept to touch base on is like the sense of weightlessness, as you saw in the video. The car was able to kind of hang in the air at the top of the loop or upside down for quite a bit of time. Obviously, not that long, but it's enough where people could sense that they're hanging. And this happens when normal force is less than the weight. When normal force is less than the weight, especially when the car is at the top of the loop, gravity is essentially the only force gravity is essentially the only force that is there. And when you have gravity equal to the centripetal force, right? Gravity makes up the centripetal force. We have right v is equal to square root of r times g, and that kind of also gives you the idea of like the minimum speed necessary in order to traverse the loop. All right. And yeah, forces, we have gravity, reactionary, normal force, or contact force, I guess. An energy principle, we have potential like kinetic energy, right? Where at the top of the loop, we're going to go back to the top. At the top of the loop, gravitational potential energy is quite large, right? And kinetic energy is actually lower. But as the cart travels down from the top to the bottom of the loop, right, speed increases and that potential energy gets transferred into that kinetic energy, and the car starts to move faster and faster and faster, right? Just going to quickly demo the glow script part of it, where here it goes. Right. And as you can see, you're going to notice from the experimental data that it is not a perfect circle. There's the little origin here, I guess that's the center of the loop, right? It is not going to be a perfect circle. And as you saw, the red ball, which represents the cart, it really hung at the top for quite a long time before speeding up back down here. Uh, so yeah, I guess the model slash experimental analysis is that the car experiences both gravitational force and the normal force when in the loop. Of course, the acceleration, it experiences acceleration slash change in speed due to like the change in direction and speed, right? Obviously, the parallel component obviously changes because the direction is always changing, and the speed, because of I guess how gravity works, right? It's going to keep decreasing in speed as it goes up the loop, right? And the component, the most important part, right? The component that allows the car to make it around the entire loop is the speed, right? The centripetal force, right? As you enter the loop, essentially you're experiencing centripetal force, which is equal to mv squared over r, and that has to be great enough to the point where it could actually, get the cart fully around the loop, right? What if the speed isn't fast enough? Well, essentially either the cart falls directly from the top to the ground, or because the cart is fastened to the track, it's just going to go backwards essentially because it just did not have the oomph to make it uh, all the way through the loop, right? I think another thing to point out is that the loop isn't a perfect circle, right? So dp over dt, the perpendicular changes, quite often, right? mv squared over r or v squared over r. The radius is is obviously changing, right? And the vertical aspect to it reduces the speed as much as possible, right? I feel like what makes the quote unquote longest hang time, what makes that possible, is that as the cart goes up, it actually there is a vertical aspect to it which reduces speed I guess, more quickly than if it was a perfect circle. And yeah, that allows the hang time to be there, and it's perfectly calculated so that it still makes it through the loop, right? And again, just to reiterate the energy principle, the kinetic energy is greatest at the bottom of the loop, right, before and entering the loop, right? And this translates to potential energy as it goes up due to the increased height, as you can see from MGH. Yeah, that was it for Full Throttle. I think if anyone experiences this ride, it's actually quite exhilarating. But yeah, that was the physics behind this roller coaster. Thank you.